Yeah. Right. Sorry for the delay. I don't know why that happened, but essentially, I'm here to give a talk on this quantum probability preservation, and I'll explain what that is exactly. So my name is Kumar Saurav. I'm here from the University of Southern California, and I'm a PhD student under Professor Lidar, who will be giving a talk later today in the afternoon as well. And this talk will consist of two papers, which are listed at the bottom, and I'll again reference them. It's always a challenge to try just to talk about one paper, so this would be harder than normal, I suppose. This will just go by very quickly. So the way that I've structured this talk is essentially I'll define and motivate what property preservation is, and then I'll talk about what the theory is, and then the results on validating this using experiments on superconducting qubits. And finally, we'll show how we apply this to get a quantum sensing advantage. So let me just get started immediately. So first, to define and motivate what property preservation is. When we say that we want to preserve a quantum state, what we usually mean is that we want to preserve a particular property of the state. So for instance, this could be something like the fidelity of the state with respect to something, or it could be the expectation value of an observable of a state, and so on. So in that sense, we formalize this as the property preservation task. So if X is the property that you were interested in, the task is essentially to maintain the property over time, even though the state might change. So we're not concerned about whether the state remains the same. We're just concerned that the property remains the same as it evolves in time. And a common solution for this is to use error correction, but that involves some other assumptions, some other requirements. Here instead, what we are trying to do is trying to achieve property preservation using an analog computational model. So essentially using smooth controls, which is why it's relevant to this conference as well. And it's interesting in a much broader sense as well, because this involves using sort of minimal resources in a way. So error correction involves a lot of other resources. You need feedback, you need measurements, and so on. And it gives us pulses. But here instead, we don't use any ancillars, we don't have any measurements, we don't use any encodings. So once we have this minimalistic resource, the only thing that we use is a smooth control. Then how do we preserve the particular property that we started on? And the setup is that we represent the target property as a function of the density matrix. So this applies, so the way I've written this is for higher dimensional cases, but I'll just focus on the single qubit case for this particular talk. But the result that I'll keep on talking about will extend nicely to higher dimensions as well. So in the qubit case, we can write the property instead as a function of the block vector, where the block vector is simply the expectation values of the Pauli matrices. And then the objective in property preservation is to keep the function of the block vector constant over time. And if it's smooth enough in time, it means that the time derivative of the function is zero. So as an example, if suppose you want to preserve the fidelity of a state with respect to the zero state, you can write the function in this particular form, which can be written in the block vector notation. And as illustrated, so if you have the green arrow representing the state that you started out with, you want to preserve the fidelity, which means you want to stay on this level set, highlighted in yellow. And your state is free to move on this yellow thing as long as, because that preserves the fidelity. You're not really concerned with whether the state is the green arrow itself or not. It just has to remain in the yellow plane as long as you evolve in time. So again, this is the central thing that we start to derive results from. And this is a different goal than quantum error correction in a way, because you usually talk about preserving things stroboscopically. But this is the last time I'll mention error correction, because this is not supposed to be a substitute for error correction in any way. I just wanted to highlight what the different thought process is behind the motivation and the assumptions that go on behind this. So, and as another highlight, so just remember, in the next few slides, I'll talk about results for qubits. but these extend very nicely to higher dimensions as well. So once we define what the task is, we need to talk about what the model of evolution is. So it's pretty generic. You have an evolution which is just described by this form, which is, I would say, well, first, let me just specialize this to the block vector case. So this can be written in the block vector form in the following way. So you have the time derivative of the block vector given as the cross product between the block vector and the Hamiltonian vector. But the Hamiltonian vector is simply you express the Hamiltonian in the Pauli basis. And then the dissipator component essentially evolves into a function over the block vector as well. So a few comments on this, that this is fairly general. This does not make a lot of assumptions, except that maybe the dissipator, this represents Markovian noise, of course, but in some cases it can represent non-Markovian noise as well. The second term in this equation, the H cross V, represents the control, and the third term represents the noise. So essentially, you want to modify your control so that the function f of v remains constant over time, given that the way that the noise acts is given by d of v. So based on this, we can start to talk about the results. And essentially, there are certain classifications that one can do. Like if you have certain target properties, you could either have properties which are trivially controllable, or you cannot control them at any point. So I'll skip over those classifications, and I'll directly talk about, given a target, a controllable property f, what is the control Hamiltonian H that preserves it? And this is one of the main results in the paper, that you actually end up getting a nice closed form expression for the Hamiltonian, which looks something like this. So it actually has a few extra free parameters, but I'll also ignore that because that's another detail that I can't really get into. So this given expression here, this essentially involves the noise in the numerator, and the function, well, it's not really dependent on the magnitude of the function, but rather it depends in the way that it's aligned with the vector itself, the block vector. And so the important thing to notice is that this denominator has the potential to blow up. So this means your control can become singular in some cases, and that can lead to a control breakdown. And if you have a potential control breakdown, if you do simulations and you analyze the problem, what you end up finding is you can have both finite or infinite breakdown times. And I'll illustrate this by an example in the next few slides, the second point. But the third point is, if you notice, the denominator is purely a function of the block vector. So because it's purely a function of the block vector, that means within the block sphere, you can denote certain areas as being regions of uncontrollability, which you can call breakdown points. But beyond that, if you're not in one of these breakdown points, then essentially this control Hamiltonian, if you apply that, your control can preserve the function over time. And the main point is this works even under the influence of Markovian noise, and in some cases non-Markovian noises. And by extension, that means it works under noise like depolarizing noise or dephasing noise and so on. And so the main thing is that there's a closed form expression that we can compute and calculate and apply. And to give you an intuition of why this particular form, essentially you had some evolution of the block vector, and you wanted to stay on this level set, which is represented by yellow. At a particular point, you are constrained. The gradient of f represents the direction of the vector, which will, if you move in that direction, that causes your function to change. So if you're at a particular point and the noise vector looks something like this, it has a component along the gradient of f. And that component along the gradient of f is the part that is problematic. And so you want to cancel that component exactly. And that is precisely what the control Hamiltonian that I gave ends up doing. So its value is calibrated such that it cancels exactly that particular component of it. And based on this figure, it's then you can sort of also think about there are certain components in the Hamiltonian that you can add, which don't really contribute to this perpendicular the direction along the gradient of f. So those are precisely the degrees of freedom that I hinted at. But again, so these are details that probably skip. To then show, essentially illustrate why or how this control Hamiltonian will work is essentially to do experiments on this to show that in theory we showed that this control Hamiltonian should preserve any property that we chose. But if we try to do this in an experiment, does it actually work out? Is it a realistic thing to apply? And so for experiments, what we tried to do was apply this control Hamiltonian specifically on superconducting qubits, which were transforms in our case. And we chose our property to be the Vx squared plus Vy squared, which is the coherence magnitude. So essentially, we were trying to preserve the coherence of the qubit during the evolution of the experiment. Even though this is the sum of squares, which is the coherence magnitude, in the end, what we ended up preserving was both Vx and Vy. So essentially, we were just preserving the coherence throughout the experiment. And the noise model in this case was simply a dephasing and relaxation at zero temperature, essentially, which is a realistic noise model for transforms. And what we then did was we chose first an initial state with a large coherence. So if you remember, the task was given the function value at some initial state, you want to preserve that particular function value. So you have a choice of what your initial coherence value is. So first, in the first case, let me just start with a large enough coherence value, and you see why this matters, whether it's large or small. But essentially, when you do that and you compute what the control Hamiltonian is supposed to look like, you get something like this. So on the y-axis, you have the price trends that you calculate from simulations. And on the x-axis, you have what the time axis. And if you do the calculations, so you get that hx and hz should always be equal to 0 in this particular case, given that you started in a state which lies on the xz plane. So essentially, because x and y don't really have any particular bias, you just choose a pure state, and then you say that this corresponds to a Vy equal to 0 and Vx equal to whatever component you have, and a Vz. So the starting point is Vx equal to something non-zero, Vy equal to 0, and Vz equal to something non-zero, corresponding to a pure state. And if you do the calculations, what you find is the y component of the Hamiltonian has to be of a certain form, which looks like this. And because this explodes here, you can reason that at this point, we should expect the Vz component to go to 0. This is what will contribute to the control singularity. So once you do this and you apply this to a given state, this is sort of the trajectory that you get. So I need to explain this plot. So on the x-axis, again, you have time. On the y-axis, you have the block vector components. And these solid lines that you see, the red, black, and purple solid lines, these are the simulations of the block vector trajectories. And so what are these? So the initial state then corresponds to Vx being something slightly greater than 0.6, Vz being slightly less than 0.8, and Vy being 0. So this is the slice at t equals 0. And then you start to apply this control Hamiltonian over time. And what you see is that these are experimental results, then the symbols squares, circles, and diamonds. So if you apply this, then you start to see this particular block vector trajectory. And then what you notice is these results, the results that you get from experiments, closely match with simulations. So these are not fixed that we had after we did the experiments. These are simply just displaying the simulation data and the experimental data. And then at this point, you can clearly see what we predicted, that the Vz will go to 0. That happens to be true. That is one thing. But the main thing that we wanted was to preserve the coherence for this experiment. And what was the coherence? Coherence was Vx squared plus Vy squared. In this plot, Vx the circle. Vz is sorry, Vx squared plus Vy squared. Vx is the circle, Vy is the diamond. So Vy independently remains 0. Vx independently remains constant. And so we end up preserving the coherence magnitude itself. So this does work. And why does this work? Why does this particular control Hamiltonian work? To give you an intuition, well, if suppose you have a given initial state, under this particular noise model, you try to saturate towards the north pole of the Bloch sphere, and you're increasing the purity of the Bloch vector. So what this control Hamiltonian will do essentially is transfer the increased purity back into the coherence. And that ends up preserved. And if you do it precisely enough, using this particular precise form, then you end up preserving the coherence. So again, this shows an excellent agreement between simulations and experiments. And if you do it with a small enough coherence, you see a different case where your Hamiltonian does not see a singularity. It instead saturates toward a particular point. And if you apply this to an initial state which had a smaller coherence, so if you remember in the previous case, the Vx was slightly greater than 0.6, here it's slightly lesser. So in that case, the behavior changes drastically. And what happens is you end up preserving the coherence for the entire time. So again, for coherence, you were only concerned with the circles and the diamonds. And that remains constant throughout time. So this works. Nice. So this is purely about the theoretical part, but then what happens if there is some particular noise in the way that we implement the Hamiltonians? And so we are trying to get into the sensing part now. So if there is some noise, you expect some deviations in the quantum trajectories, which means if you have certain deviations, you know what these deviations are, then you start to use these for quantum sensing. And the specific noise that I'm talking about is a small static external field. And why is this particular noise model important? Well, this is important because this models any qubit frequency miscalibrations. So any miscalibration that you have that appears as a detuning, which is essentially a small static external field. Or you could also use it for medical fields or biomedical applications, which already have a lot of extensive literature. So the main thing is, yeah. So if you apply an ideal Hamiltonian, this is sort of the Bloch vector trajectory that you would expect. So Vx remains constant, Vy remains constant, Vz decays to 0 if you have a large enough coherence. But when you have an external static field, you start to see these deviations. So I've not really quantified what the deviations are in mathematical terms in this, but it will be done. It was done in the paper. So I'll just give you a qualitative view of what is happening around you. So essentially, this particular Vy that you see, that sees a large response to the external noise that we have. And so what this means is we can use this deviation Vy as a signal for this external noise delta. And prior word for this is the standard way to measure this delta term is to do it via Ramsey interferometry, which essentially is you prepare a plus state, you apply a pulse, you prepare the plus state, and you let it freely evolve, and then you see what the trajectory is. And that gives you Ramsey fringes, that gives you what the detuning is. And the max signal, if you this is the sort of max signal that you get in mathematical terms. So then the question is, if you apply the control Hamiltonian that we propose, and you have a deviation delta, a noise characterized by delta, is the signal bigger than this particular value? And of course, the answer is yes, otherwise I wouldn't pose this question, but essentially, if you do experiments, so again, this is the experimental data, and the plots here show on the x-axis time, on the y-axis signal. So the Ramsey signal goes something like this, which peaks at this particular point. And the signal that we get goes something like this, which peaks at a much higher point. So essentially, there is an improvement. So the way to compare would simply be to take the peaks, see what the ratio is, and that gives you the improvement ratio. In the particular experiment setup that we had, we saw a ratio improvement of 1.65. And in fact, theoretically, you can go up to a 1.96 times improvement in the SNR for this particular tuning. And theoretically, you can show there's an unconditional enhancement. And the main advantage of this is that you don't require any extra resources to complete the sampling task. So it's applicable in just about any system where you can apply smooth controls and you can do measurements. And that's the only thing you need to have the signal boost. And again, this is important in cases where you have, so it's important in cases where you have, where you need to be really precise about your detuning in the qubit frequency, for example. And that basically concludes my talk. I'll just leave it with a summary slide. I don't really have time to go over this, but that's it. Thank you for listening.
Any question?
Thank you very much for this very nice talk. I have a couple of questions. The first one is very quick answer. Which qubits did you use for experiments? What did you use for experiments?
Transpons?
What quantum computer? What company?
Oh, so we have an experimental group at USC. So we just collaborate with them. It's Levenson-Falk's lab at USC.
The second question is, in order to get this Hamiltonian, you need to know the noise operator.
Yes.
So how do you know the noise operator for that?
So for the computers in his lab, so I think they already knew what the noise model was supposed to be based on the experiments that they have done. So they have characterized what their setup is, and then they know that only the parameters of this particular thing change. And so they perfectly calibrated this in a sense. So they knew exactly what this noise thing is supposed to be. If you don't know anything about the noise, then of course this entire theory that I described does not work out because you need to know that precisely.
Yeah, very, very interesting. I had one question. So the Hamiltonian derived, so basically you assume that you only have unitary control, right?
Sorry, can you repeat that?
Sorry, the control that we have over the qubit is all unitary via the Hamiltonian.
Yes.
But basically it seems, or it's, yeah, have you considered what about if you assume some sort of non-unitary control? If that might help, because it seems like with these manifolds that you're trying to stick to, that like the uncontrollable regimes are somewhat related to that you cannot fix that part of noise or whatever with the unitary control also only, right? So are there any schemes for non-unitary control to fix errors like this?
So one way that we are thinking of trying to extend this or generalize this is using measurements or weak measurements precisely. But I haven't really thought of any other sorts of non-unitary controls to extend this. But maybe if you have anything, we can discuss after.
No, measurements would have been the first choice.
Okay. Yeah. But then basically that's one of the future works. I think I have a slide on that, but again, that was supposed to be an extension of this. Yes.
Okay, thank you.
Okay, thank you again to the whole of the presentation.